I changed the battery. Yeah, in international group, you need to lay the class. Actually, I also couldn't join the next one day because I have a TA meeting with my professors. So it's no problem. Okay, I had that notification too. Yep. So no worries about it. Let's start today's class. Today we will study about some fundamental spaces on a matrix. So the main title is same. We are learning general vector space. And today's section is row space, column space, and null space. From these spaces, we will calculate some notion of rank from this space and nullity of null space from null spaces. Simply, that is the dimension of the spaces, and we will construct that, and why I said row space and column space are same rank, because it has same dimension, and we will talk about it. Firstly, today I will use capital A is n by n matrix, if I do not say others. Then we might be able to express the entries on A, A11, A12, A1n, A21, A22, A2n, and so on, N1, N2, AMN. And then we already said that the horizontal line is row and the vertical line is column. So simply the row space, to construct the row space, column space, it is we will divide the row vectors and column vectors. That means the vector A11, A12, A1n, A21, A22, A2n. In the same way, we can define Rm, Am1 to Amn. And these are coded row vectors. And I will say the space generated by, I will denote generated like this bracket. I want to Rm is the space, row space is the row space of A. Similarly, you might be able to construct the column vectors if you define C1, A11, A21, AM1, and Cn, A1n, A2n, AMN. And then we also can think about this is will be called the column vectors, and the generated space C1 by C1 and C2 Cn is called the column space of A. That is row vectors, but when you think as a vector, you might think the transpose. Well, it is to express as a vector, you need to see it is a column vector, but we just seeing row vectors, and although you gather like the row vectors, it satisfies the all axiom of vector space. So simply, if you calculate some linear combination in these vectors as the entry as the addition and multiplication for entries, then you can calculate the linear combination of each vectors. C1R1, C1R1, C2R2. Oh, I think that is not good notation. Here's denote D1, D2, DM, Rm. If you construct a linear combination of this space, then it will enter in here. We just gather these elements from the spanning set. If you feel hard to understand, then simply you think the transposed vectors. We use LU row vectors. Yeah, we use row vectors. Yeah, right. Although you do not take transpose, it will be vector as the element in a vector space. Let me write large R. It does row vector space. It will have an element from R1 to Rm with linear combination, and you just think as a n-tuple element, A11, A12, A1n as a tuple, then it is an element in R to the n, right? If you consider a vector space over R. So the row vector or column vector is one expression of a vector. You do not know the real what real vector is. This is yeah. column. Yeah, that is right. And we also can yeah, we can consider in a vector space because we have natural correspondence like A1, A2, AN. This is row vectors, and we have one-to-one correspondence to column vector. Just it is not same element, but to express that vector, some vector V. We were not given. We do not need to everywhere always. We do not need to always because column vector is just an expression of a vector. Column vector is not a real vector. Yeah. Column vector is expressed vector. So actually, when you see an element in R to the n, we usually write these elements as a column vector. We might use an, but actually it is an expression over a standard basis, and we defined the standard basis of R to the n as 1, 0, 0, 0 is e to the 1, 0, 1, 0, 0 is e to the 2. We defined this standard vector, and we will consider the coefficient of the basis linear combination. A1, A2, AN. So we expressed the vector to column vector, but of course we can express to row vector. Yeah. If you choose just the expression of row, then it is a same vector V, but the V vector can be expressed A1, A2, AN as a row vector. It is a kind of just expression of V. V some basis vector. And also we can express V as a column vector. It is one expression, and usually we consider the row vector is an equation and column vector is an element of vector, because we defined it. As I just said, the row vector is equation, and the first element is A1, and second coordinate element is A2. Like we say, we defined each coefficient, and then it will give the vector position in the space. So column vector means an element of vector space. That is true, but when you consider the equation, then that means we might think it is equation space as a vector space. Equation. The equation. Because as I said, the row vector can be regarded as equation, and if you gather all equation linear combination with these equations, then it will be satisfied the axiom of vector space, like addition is associative and commutative, something. We have 9 or 8 axioms, and if you gather just these row vectors, if I say, in other words, you gather all equations, then it will give a vector space. Just linear combining the equations. So it is also true expression, although you do not have transpose. But to understand the vector space, it is easy to consider transpose, because the row vector space has one-to-one correspondence to column vector space. Vector is just an element of vector space. So a little important, because usually we have this notation with equation and elements. So it is a little important, but to understand it as a vector space, row space and column space are vector space. And in this sense, you do not need to consider what is row, what is column. Just I want to note it on, it is vector space in R to the n and R to the m. Row space will be in R to the n, it will in R to the n. It will consider as a tuple. And then we saw that the row space and column space. So let me see the null space. Null space is simply the space of solution set of a homogeneous equation. If you have an equation, if you have a matrix A, then you might be able to construct a vector, linear equation AX equal B, given B, and but if you consider non-zero vector B, then if you collect the solution sets some n of A, then it would not be a vector space, as I said before in the last class. But if you consider AX equal 0 homogeneous case, in this case, if you gather all solutions X, I will say n prime, and it is n A, n E A. That means this is n 0 A. It is not important. If you consider the solution space of a homogeneous linear system conducted by the matrix A, it will be a vector space. Then it is also a kind of important subspace. We can regard as a subspace, and we will say that is null space. The solution space of the homogeneous system of equations Ax equals 0, then we will gather the element x, and to calculate A multiplying x, we should have x0 x1 to xn, so it is in R to the n. So the space is a subspace of R to the n, and is this solution space is denoted null A or just n of A, and is called the null space of A. The null space of A. So when you have a matrix n by n matrix A, you can always get the row space and column space and null space as well. If the A equals to 0, then that is a good question. When A equals 0, then the homogeneous equation always will have all vectors can be a solution, because when you construct Ax equal 0 as a matrix, then it means 0 matrix multiplication on x1 to xn equals 0. And if you bring any vectors in R to the n, it will satisfy this equation, right? This linear system. Then, if you gather all solution is just same to R to the n. So it is also can be subspace in R to the n, and also you can find the null space even the matrix is 0 matrix. That is true. So in this sense, if you have a matrix A and a vector X, so you will find the homogeneous equation solutions. That means what vectors can be collapsed in transformation A. So if you have a three-dimensional vector, and when you consider A is just what was it? Not case to 0. to XY plane. When it's like a collapse, if you consider a projection, I just forgot the name. If you consider the projection to XY plane, then when you consider this vector, x will go to this vector from A to the x, A of x. But when you consider the z vectors, z line, from vector space in z line, it will be go to 0 vector. Then the solution set will be same to the z-axis. In this case, so actually finding this null space and some row space, column space, to calculate it, you need to calculate the matrix and the linear system, and so it will take. Actually, eventually we will use Gauss elimination to find the solution, and so that is the reason why we studied about it. The null space is the solution of Gauss elimination. It is just true. That is nullity. I will. When you consider the dimension of null space, then you will get some number. What? And I just like n, and it will be nullity. And yeah. So we need to run row column space. We'll make rank as a dimension, and null space will make nullity as the dimension. So then we might ask the relation among the spaces, row, column, and null space. Let's talk about it. Firstly, let me introduce a theorem. As I said, if you gather the solution set of this linear system, then it will not be a vector space. But considering the solution set is also, we need to consider the solution set as well. And a linear equation ax equal b is consistent. Consistent means that having at least one solution. At least one solution. If and only if the vector b is in the column space. Of A. So now we can see property of column space. Simply, we can prove it. Let's firstly consider B is in the column space of A, and let C1, C2, Cn are be column vectors. Vectors of A. If you assume the x is a consistent, then you have R to the n vector, and let me assume if we assume that x0 0 x1 to xn is a solution of the equation of the linear system x to the b, then ax0 will be the linear combination of column space, because when you calculate the matrix multiplication, x1 will multiply to the first column vector and x2 will multiply to second column vector. So it will denote, I will denote 1 from 1 to C2 xn Cn. And we said this x to the x sub 0 was a solution of this equation, so it is same to b, and so it is in the column space of A, because it can be written a linear combination of C1 to Cn. Conversely, if you consider the B in here, then naturally, in the same way, you can get the x coefficient by representing the B to the linear combination of C1 to Cn. So actually, this event only let me see an example. Linear system is minus 1, 1, 2, 3, 2, 1, minus 3, minus 2, x1, x2, x3 equal 1, minus 9, minus 3, and then the example is just show that it is in column space, because it will be in column space means the linear system has a solution, at least one solution. So by finding the solution of the system, linear system, we will show that B is in the column space of A. And if I cheat, I will not calculate here. By using Gaussian elimination, you might have the reduced row echelon form. You will get a row echelon form, and it will give the solution x1 equal 2, x2 equal -1, x3 equals 3. Actually, if you calculate this, 2 minus 1, 3, 2 minus 1, 3 is 1, and 2 minus 1, oh, just 2. 2 minus 1, 3 is good, is -9, and 2 minus 1 minus 3 is b minus 3. Yeah. So it is the solution of this linear system. And since you find a solution of the linear system, B will be a linear combination of the column vectors. Like really, B can be written 2 minus 1, 1, 2. This is C1. And -1, C2. 3, 2, 1, -6. Oh, not minus 3. Plus 3, 2, -3, -2, 0, -1, 1, 2, 3, 2, 1, 2, -3, -2, okay. Then if you calculate it, of course, it has the same calculation, so it will be denoted to -2, -3, +6, 1, and as we calculate in here, you can get the solution B with the linear combination of column space. And so in here we just so that the one expression of here usually often we have find that when you see the space, column space or null space, you might want to get the basis. Then we need independency. To explain it, I will mention one theorem. If x is any solution of a consistent linear system, linear system A x equal b, and if S be a set we want to be K, which is a basis for the null space. Over A. Then every solution of the linear system. Ax equal b can be expressed in the form, as we see that if you have one solution, then another solution x, every solution x will be written x0 plus linear combination of null space v1, c2, v2. Let me write d1, d2 because of the notation of c1s. di's are each di is in base field R now. dk, vk. And conversely, for all choices of scalar d1 to dk, the vector x, if you bring this element x, then it will be solution that I mean the null space will give the solution space, although it is not in a homogeneous form, because the equation just the solution set of this linear system will be constructed by translating from the solution set of here. Because if you, in some sense, there is a solution x0, and editing the solution from here v, it will be a solution set in here. And conversely, if you consider only this vector in here, and by deleting the vector solution x0, you will get the homogeneous equation. So it is just translating by x to be 0, x sub 0 as a proof. It is same in the proof. Let v be an element in the null space of A. Then you can calculate A x0 plus v is ax0 plus av, and v is in the null space of A, so it is 0, and in our assumption x, I will write bold x0. x0 was the solution of the linear system, so it is B. That means x0 plus v is also a solution of the linear system ax plus ax equal b. So it makes sense. And conversely, if x be any solution of equal b. Then we said x0 will satisfy this equation. So a x minus x0 is a x minus a x0, and if a x0 was b, and it was x be a solution of this space. So let me write below side ax equals 0 because of this assumption, and ax0 was b, and so the x minus 0 will be in null space of A. So conversely, if you bring any solution over here, x, it by translating x0 vectors, then it will in the null space of A. So this theorem is explaining that although we are defined the null space of homogeneous equation, it is also the can be expressed in any linear system. And previously, when I start this topic, I said we will find the solution from Gauss elimination. When we calculate Gauss elimination, we only use the elementary row operations. So we need to calculating row operations will not change the won't change the space of row space and null space like that. Of course, the column space will change by row operation, but it is not important to consider the rank, the dimension. Firstly, row equivalent matrices, that means some row equivalent. If two matrices A and B are row equivalent, then they have the same row space. Similarly, these matrices have the same null space. I prove first one. If let me write A and B are row equivalent. Are row equivalent, then that means when you choose one matrix, if I choose matrix B, then B can be obtained by multiplying elementary row operation. Let me use this simple elementary row operations from A. that means this row of B if you choose some ith row of V, it will be calculated from the linear combination of A because the elementary row operations means exchanging or some multiplying to others and some multiplying itself of the row. That means multiplying itself is just multiplying some scalar, and exchanging will just if I row to J, then it is just A's I row, and so it will be denoted by the linear combination of A's rows. I mean the rows of B could be expressed by a linear combination of the row of A, because linear elementary operations means just linear making linear combinations. And conversely, if you choose matrix A first, then A could be expressed by the matrix, the rows of matrix B. So the row space it means if you consider the row space of A is the row is V1 to Vm, and the row space of A it was W1 to Wm. We expressed the linear combination of V1 to Vm to express W1 and Wm. That is the way of from B to A, from B to A by making this way, and conversely by constructing linear combination of W1 to Wm, you could get the vectors V1 to Vm. Then the main the spanning set is the same. So the spanning set was row spaces. So the row spaces of A and B are same. Okay. And similarly, null space is also the same. We are as a vector space. It's same row space. This row space was just the spanning set of row vectors. And here, when you bring the row vectors, and we defined it row space as a linear combination, linear spanned space of these m vectors. same mean as a vector space? Yes, all element is same. Yeah, we expressed the A's row vector space was change and transform expressing as a linear combination. Transform is okay. The transmit. That sort of makes it makes sense. I will add explanation. The row space of A is, if you write A1, A2, AM, and B1, B2, Bm is row vectors, then the row space is the spanned spanned by these vectors, and the row space of B is spanned space by B1, B2, Bn. Okay. B1, Bn. Then if you construct the vector B1 to Bm from the linear combination of A1 to Am, like B1 was C1 A1, C2 A2, C1 A1, C1 to A2, like this way, C1 M Am, and Bm was Cn1 A1, Cn2 A2. If you are able to express as a linear combination of A, span this space, Cnm Am. This means the spanning set of here, that means B is a subspace of A, because all spanning vectors can be expressed by the linear combination of A. And conversely, if you are able to express a linear combination of B to express the elements A1 to Am, then it means A is subspace of B, and so if you combine two vectors, the row space is really same as a vector space. The space case is also same, and I think the proof is easy to after you learn the property of rank row space and null space. So let's see an example. We'll find I skipped. Theorem and then we might need to, by using this notation, then we can think about that if you if you express the matrix A, to reduce echelon form, because it is simple form of matrix. From here, you can get row space and null space easily, because it has the form of leading one and others. When you see just row echelon form, it will noted like a tear. Here is not zero. One something. Here's zero. One something, like this form. It was a row echelon form. Zero. Here's zero. It was row echelon form, and in here you can see the row space easily, because you just calculate. You are able to calculate what rows have leading one, and we will not consider the zero rows, because by editing or by to calculate something, it will not change the row space. So in this case, we can get the row space easily. And also this theorem is saying original matrix A will have same row space with the row echelon formed matrix. So the row space of row echelon forms. And so we need to only consider how we can get the row space and null space of row echelon form. If a matrix R is in row echelon form, that means in the form of here, then the row vectors with the leading one form a basis for row space of R. And also we can think about the column space. Of course, it is not the although it is not the same, we can consider it. And the column vectors with the leading ones of the row vectors form a basis for the column vector, column space. is same what I said. When you consider the row space, you will not consider the 0 rows, so it is enough to consider the leading ones having leading 1 rows. It will, and also this form of basis of row space of here, because under leading 1 it does not have any entries. Its entry is 0, and that means it is linearly independent to other row vectors, and so on. This second row vector will linearly independent to other vectors, and so on. So the row space will spanned by all row vectors, and it has the linearly independency, so it forms a basis. In the same way, if you consider the column vector, when you consider the leading ones, it is here. In this case also, other elements will be written on the right side of leading ones, and then by linear combination to other leading ones column vector, you can construct other columns, all columns, as a linear combination of leading ones column vector. That means it spanned all column space, and also not only span the space, it will be a basis because the leading term will happen in another row, so it has linearly independency. Because the column vector is just element standard basis form. Here, E1, E2, E3, E4 is the column of leading one. The row like this row equivalent matrix give a useful tool, and so I will explain more about it. When you see the previous theorem, always the row space the leading ones will give the basis of row space, and additionally, the leading ones also will give a basis of column space. That means the number of leading ones will not change it, so that the dimension of the row space and the dimension of column space will be same. And to make it sure, let me give this theorem. Equivalent matrices then given set of column vector is linearly we just said so the row echelon form, but we will extension to the any row equivalent matrices. So A is linearly independent, depend only if the corresponding column vectors of B are linearly the set of column vectors is linearly independent. I mean typo. And also we'll see the dimension. Let me we'll see the spanning basis property. In the same way, if the column vector, a given set of column vectors of A forms a basis for the column vector, the column space of A, if and only if the set of column vectors of B form a basis for the column space of B. Then I will prove just A, because it is just row operate with elementary row operation will change all column vectors, like when you consider the column space, it means this spanned by column space will go to the column space of B, because when you consider matrix A and when you consider the column space of A, the row elements will calculate all elements in a ith row to others, and so we will make a vector B, the matrix B, and then the span set will also just, when see one column vector, it is linear combination of each entries. It will not change the dimension of spanning set. So if you consider the linear independency, then the statement B makes sense. So to verify the linear independency, we already saw that if D1 prime was C1 W2 prime. If you consider linear combination, here D is a scalar and W I prime is each W I prime is a column vector. Of B. Then, as I said before, since B is a linear combination of row, by calculating elementary row operation, we will get a matrix A. So, if you denote it a linear system, D1 to dk equal 0, then its row operation, elementary row operation will not change the homogeneous part. Elementary row operation will not change the right side parts, and so if some column vector, if W1 prime and 2WK prime were linearly independent, then with the same coefficients, dW1, d2W2, dk, wk, equal 0 here, wi, each wi is a column vector of A. Because it is just by calculating row operations, elementary row operation, we will change here row vectors, then we can make W1, W2, WK, and also, but the row operations will not change the columns. That means D1 always will multiply to D here, and D2 always multiply to here, and dk always multiply to the kth column. So the left side will give the linear combination, and the right side always give the zero vector, because the elementary row operation will not change the zero vector. And in the assumption, we have A is linearly independent, A columns linearly independent, so D1, D2 to dk are all 0. Columns of the set of column vectors of A is linearly independent. Thus, we started from the linear combination of here, and we get the all 0. That means B is linearly independent. The set of column vectors of B is linearly independent. And conversely, if you bring the linear combination of A, then it will B, and so from B, A is linearly independent. So it is with an only if property. So if you have two equivalent matrices, then it has linearly independent. If one matrix has linearly independent column space, column vectors, then another one is also linearly independent, and it will be a basis as well, even if it will be basis. I think let's take rest time. Actually, I prepared one example. No, this explain when you while you make Gauss elimination, it will not change the dimension of row space and column space as well. This theorem want to say about it, and so let's see an example. If A be a matrix 1, 2, 2, minus 1, minus 3, minus 6, minus 6, 3, 4, 9, 9, minus 4, minus 2, minus 1, minus 1, 2, 5, 8, 9, minus 5. Okay. We don't need more. From this matrix, we will calculate the Gauss elimination form. In here, by editing to the first row by first row, then the one is same, and the last row will be 0. Yep, multiplying 2 and subtracting this, it will reduce this line 2. Then let me write it together. For the second row, we will calculate second row minus 2 first row to the second row, and for the third row, we will calculate minus 2 first row to the row. Then it will give 1 and 4, 3, minus 10, minus 2, the rest. And the third row is the third row will be 0, 0, 1, 3 is same, and minus 1. And we can calculate one more from third row by subtracting second row. It will give a matrix minus 3, 0, 0, 0, minus 4, 1, 0, 0, minus 2, 3, 0, 0, 5, minus 2, 1, subtracting 1, 0. It will give this row echelon form. Right. And then to calculate the row space, we just use only row operation. it will not change the row space of A. In here, if you define the rows from arctic1 to arctic4, then the row space of A is same to linear span by R1 to R4, and it has different row, but you just we only use the row operation. That means we didn't change it first row, so it is row 1. And when you calculate find the second row, that was R2 minus 2R1. We calculate it to R2, and the third row was R3 minus 2R1, and the last one is R4 plus R1. It is I didn't calculate it. R3 minus R2, R2 minus R1. Okay. Now R3 minus R2. Okay, thank you. Then calculate it minus R3 plus R2 minus R1. In this way, we get another row, but if you consider the row space, then it will span by R1, R2 minus R1, minus R3 plus R2 minus R1, and R4 plus R1. Then, as you can see, the space is same, right? Because by using the linear combination of these elements, we can express all element generators. And conversely, from here, by using linear combination, we can express each generators in here. So the vector space is same. So to calculate row space, it is easy to calculate from here. Then it is easy to calculate from here than from here. So we will calculate it, and in your case, the row vector space is 1 and 3, 4, and 2, 5, and 0, 0, 1, 3, minus 2, 0, 0, 0, 0, 1 is the row space of A. We already see for here, since we saw for an example, it will make sense on every matrix, m by n matrix. And also, when you consider the column space, of course, column space will not same to the column space of A, because we use the row operation and it will change the column space. But when you consider the linear independence or the dimension or some information of vector space, in here, the column space would be spanned by the three vectors having leading ones, because the column space will spanned by 1 0 0 0 0 1 0 0, or in here is 4, and 5 minus 2 1 0. This will span similarly. It's 1 0 0 0 0 1 0 0 0 0 1 0, and another, if you see another column vectors, it will be expressed from this elementary row element standard basis, like a standard basis. And we didn't change the column. Since we didn't change the column, it will bring the same column first, third, fifth, first, third, fifth will form a basis of column vectors of A. That was the last theorem. Form of basis, and it is also form basis of B. Here B is low echelon form. So these three vectors will span column space C2, C4, C5, then C1, C2, C3, C4, C5, spanned by these are same to spanned by 5, and also it will form a basis for the column vector space, column space of A, because of this theorem.